Oh,
Hello everyone, this is Team Shumin Jiang and Edward Xie He, and this is our final project. I'm Shumin Jiang from the Friday 2:30 class and introduction.
and this is Edward He. Our team, our team name is Bagel Tastes Like Sense. And let's Minjiang introduce what we done.
Okay, so first is the outline. We'll introduce what we have done and our future plan and what we have learned. So the first part we have the trivial part is autocomplete and get position. So this two part was easy. So I just show the running results. Like for the autocomplete part, we got a TRA and we have those four results. And for the find location, we input Trader Joe's and it gave us the latitude and longitude. And next we got the calculate edit distance. So we have so I write two methods, one with memo and the other without memo. For the with memo one, the time complexity is O n square. And for this one, I create a 2D vector as the memo and to store the result of di-1j, dij-1, and di-1j-1. And I got my dij as the 1 plus the minimum of those three. And this is the with memo one, and I got the without memo one. For this one, I use a recursive function with the calculate edit distance without memo. So run it again and again. Like I test with the example, welcome to USC and beat UCLA. So the result was 10, and the with memo one only takes 327 microseconds to pass the test, but the calculate edit distance without memo never give me an answer. And next is the shortest path. And
And this part we use two classic algorithm, Dijkstra and Bell-Manford, to calculate the shortest distance between two places. And for Dijkstra, we established a priority queue. It's a minimum heap to save the runtime. For Bellman, takes more time because it needs to visit all the nodes. And we find some tips to improve the Bellman forward with early terminated if all the nodes are the same. And next page, we just have some results compared to the Google search. It, technically, it just the same, but Google have different transportation methods to choose. So, and we find sh uh, shortest path from CVS pharmacy to Trader Joe. It's a very not very far, and Ruff's to Trader Joe. It's a midterm. It's a midterm far. And from Trader Joe to Whole Box, and the Trader Joe to Dirt Dog. Uh, uh, as the PPT shows, they just looks like the same. And the next page,
mhm.
and next page is the runtime analysis. Dijkstra takes less time for run, maybe 246 milliseconds, and as shown in the PPT. And the time complexity of the Dijkstra is O E plus V log B. It is faster than the Bellman-Ford O E multiple V because Bellman will visit all the possible nodes until it finds and stop. For Dijkstra, we use a high priority queue so it is faster to quicksort. Um, so for And for Bellman, we use on the ordered map to store every neighbor's visited until we find the path. So it takes lots of time. And next page. It's a psycho detection. We use Boo uh, to return is it in or out the square, and we got a sub graph, and we don't even need to plot the cycle to do a cycle exists or not. So it is also a DFS processing. So we travel all the nodes with a subgraph. If there is a cycle detected, the DFS visit its neighbors. Not if they are not parent nodes between two nodes. So we can say there is a cycle. And because it is a DFS processing, so the time complexity is O V plus E. And next page, it's a cycle detection result. We've just find the larger square range that we can find the cycle exists, but in the mini square range, no cycle exists. And next page is a topological sort deliver children problem. We just rated the dependency and names, mark locations, and DFS processing again. If there is a cycle in the topological sort, we just return the empty vectors. So there were some cycle cases to show in the picture, and we do extreme cases like it's a circle, so there is empty vectors, and because it is DFS again, so the time complexity is OV plus E. And the next page.
Okay, so I'll introduce the TSP for you. So TSP is a very interesting part. So first method is the brute force, and it's like DFS search and doing this for all nodes and try all things and get the minimum one. And the next we got brute force with backtracking. So this one is like faster, no, it's faster than the last one since it's used backtracking, and we like check the current distance with the shortest one, and if it's like larger than the already shortest one, so we'll abandon this path and all paths based on it. And the next is the 2OP1. It's a very good method, I think, that like we got an initial path and swap a pairs of two nodes and check if it makes the path shorter. So like if it makes it shorter, we can choose the new path and do 2OP again and again until we find the shortest one. Like any swap cannot make it shorter. So I'll compare the algorithm, and so this one is the number of places. Like we try 8 place, 9 place, 10 place, and 11 place. Unfortunately, the 10 place and the 11 place takes like more than 10 minutes to run, so I couldn't give the data. But for 8 places is, and we can see here is the microseconds for those 3 methods, and here is the resulting miles, and then for the 9 places. And we can see the backtracking ones is faster than the brute force one, but the 2OPT one is the like fastest. But for the result, we can see brute force and the brute force with backtracking get the same result, but the 2OPT one get the like larger ones, makes it like the accuracy part. The 2OPT one is not good as the brute force one and backtracking one. And the next part is the find nearby. So we haven't done this yet, but we got a future plan for it. Like we want to use a min heap based priority queue to store all the results and give at most k results, but it can be smaller than k, but like in the circle generated by the radius r as the inputs of it. So what we have learned from that is first we learn a lot of DFS method since like at least 3 or 4 parts need to use the DFS, and the heap and queue. This this like we can use heap and queue to save our time for the method. It takes like although it takes more like complexity, but it has smaller like make it faster. And we also use a lot of BFS. And that's all. Thank you guys.
Thank you.
I need to stop.